Good morning, folks. I just want to continue where we left off yesterday with these polar coordinates. I didn't want to make the video too long and crunch everything in one, so I decided to split it. So continuing to move forward, polar coordinates, it's basically still mapping to a position, right? We're going to think about a two-dimensional plane, and rather than a set of horizontal and vertical rectangular coordinates, we're now using a distance and an angle of rotation. So on the slide in front of you, you're going to notice that we have this point on this plane where I can get there one of two ways. I can take a horizontal x, a vertical y, and I get there some arbitrary position. Or I could stretch out a distance and rotate up a theta and get there as well. And if you think about that, it kind of combining both coordinate systems makes this little right triangle of x, y, and r theta. So if they're both mapping to the same position, there's clearly a connection between the rectangular coordinate plane and the polar coordinate plane. Hence how we can convert from one system to the other. And it's really not that difficult. So let's start from polar to rectangular. So I would be given r and theta, and I want instead to make an x and a y. And it's quite simple. So think about it. If I think about this as this right triangle situation, r is essentially the hypotenuse and theta is one of the angles. Now we're going to assume that a right angle is always present because again, the x and the y are perpendicular. So there is always kind of an implied right angle here. And I would simply take r times cosine theta would give me the horizontal leg, aka the x coordinate. R times sine theta would give me the vertical leg, aka the y coordinate. Now, obviously, there's going to be a handful of positions where we don't have a nice, perfect right triangle, all right, those four quadrantal positions. However, this conversion does hold for everywhere on the coordinate plane. My metaphor of the right triangle doesn't, but it does hold most of the time. So a quick example, if I have the polar coordinate plane or coordinate point, excuse me, 2 comma pi over 4, a very quick and simple conversion to rectangular coordinates would be 2 cosine pi over 4, 2 sine pi over 4. And of course, I would expect you to simplify this in exact terms. Whenever possible, leave it in an exact term. Obviously, if we had 46 degrees instead of 45, we would require a decimal. So flipping this around now, let's say we would be given an XY ordered pair, and we want to now convert that into the R theta ordered pair for polar coordinates. So think about a right triangle that you know the horizontal and the vertical leg for, and we want the hypotenuse. Well, a very simple formula comes into play here. We have the Pythagorean theorem that connects x, y, and r are literally the three legs of this arbitrary triangle. So we have one way using x and y to solve for r. Theta, again, think about this as I am given, excuse me, I have the opposite and adjacent legs of a triangle in which I want the angle theta. Well, opposite and adjacent, obviously we're going to use a tangent ratio. Because we're solving for theta, it's going to be an inverse tangent function. Obviously, this is only going to hold when x is not 0. However, if x does take on a value of 0, I'm going to allow you to use a little bit of just quick reasoning. I mean, think about it. If x is 0 and tan inverse becomes undefined, there's only two positions on the coordinate plane that would satisfy. So you're looking at either pi over 2 or 3 pi over 2. For every other value x, y, we're going to use tan inverse. So let's see now. We have a rectangular ordered pair, -1, comma, rad 3. So there's my x and y. So do a quick, I'm going to solve for r, so obviously we're going to take an absolute, or not an absolute value, a square root of x squared plus y squared, plugging in carefully. We get a nice value of 2, okay? Tan inverse of y over x becomes tan inverse of negative rad 3, negative square root of 3. And tan inverse of negative square root of 3 is negative pi over 3. And this is the one stop in polar coordinates you want to be very careful. You always want to consider positioning. So if I'm considering negative 1 comma square root of 3, what quadrant is that located in? A negative x, a positive y. That's a quadrant 2 ordered pair. If I think about r comma theta, where r is 2 and theta is negative pi over 3, that's going to put me into a fourth quadrant position, right? If I go 2 over on the x coordinate and then rotate negative pi over 3, that puts me down into quadrant 4, which doesn't uh, agree with the rectangular coordinate plane. So simply put, we want the other inverse position for tangent. Keep in mind, inverse trig functions have those restrictions. Tan inverse only operates, or I should say only maps to quadrants 1 or 4. It's never going to give you a quadrant 2 or 3 position unless you rotate into there. So with the theta, you might need to take the other position if it disagrees with the quadrant. You always want to just confirm that the positioning of your polar matches the positioning of your rectangular. Okay? And as long as it's the correct quadrant, they're going to match. It's not like they're going to both be in quadrant 1 but not equal each other. So this was a pretty straightforward 2 comma 2 pi over 3. This is a pretty straightforward conversion for these two. We are going to do a little bit more with these conversions in terms of equations, but I'm going to save that for tomorrow's video. So check back on in the problems on the textbook. Reach out with any questions you might have, and be good, be safe. Enjoy your afternoons, folks.